The answer would in part be found by German scientist Rudolf Clausius, and it would form the basis of what would become known as the second law of thermodynamics.
Rudolf Clausius was a brilliant German physics student from Pomerania who studied in Berlin and at a ridiculously young age became a very brilliant professor in Berlin and then in Zurich at the new technology university set up there in Switzerland. And in the 1850s and 60s, Clausius offered what is really the first coherent, full-blown mathematical analysis of how thermodynamics works.
Clausius realized that not only was there a fixed amount of energy in the universe, but that the energy seemed to be following a very strict rule. Put simply, energy in the form of heat always moved in one particular direction. This insight of his is in fact one of the most important ideas in the whole of science. As Clausius put it, heat cannot of itself pass from a colder to a hotter body. This is a very intuitive idea. If left alone, this hot mug of tea will always cool down. What this means is that heat will pass from the hot mug, say, to my hand, and then again from my hand to my chest. This might seem completely obvious, but it was a crucial insight. The flow of heat was a one-way process that seemed to be built very fundamentally into the workings of the entire universe. Of course, objects can get hotter, but you always need to do something to them to make this happen. Left alone, energy seems to always go from being concentrated to being dispersed.
One of my favourite statements in science was made by the biochemist Albert St. George, who said that science is all about seeing what everyone else has seen, but thinking what no one else has thought. And he, Rudolf Clausius, looked at the everyday world and saw what everyone else had seen, that heat does not flow spontaneously from a cold body to a hot body. It always goes the other way. But he didn't just say, ah, I see that. He actually sat down and thought about it.
Clausius brought together all these ideas about how energy is transferred and put them into mathematical context. It could be summarized by this equation. Now, what Clausius did was introduce a new quantity he called entropy, this letter S. Basically, what it's saying in the context of this equation is that as heat is transferred from hotter to colder bodies, entropy always increases. Entropy seemed to be a measure of how heat dissipates or spreads out. As hot things cool, their entropy increases. It appeared to Clausius that in any isolated system, this process would be irreversible. Clausius was so confident about his mathematics that he figured out that this irreversible process was going on out there in the wider cosmos. He speculated that the entropy of the entire universe had to be increasing towards a maximum, and that there was nothing we could do to avoid this. This idea became known as the second law of thermodynamics, and it turned out to be stranger and more beautiful, more universal than anything Clausius could have imagined. The second law of thermodynamics seemed to say that all things that gave off heat were in some way connected together. All things that gave off heat were part of an irreversible process that was happening everywhere. A process of spreading out and dispersing. A process of increasing entropy. It seemed that somehow the universe shared the same fate as a cup of tea.
The wonderful thing about the Victorian scientists is that they could make these great leaps, and that they could see that their study of a thermometer in a beaker actually could be extrapolated, could be enlarged to encompass the whole universe.
As Boltzmann stared into his brave new world of atoms, he began to realize his new vision of the universe contained within it an explanation to one of the biggest mysteries in science. Boltzmann saw that atoms could reveal why the second law of thermodynamics was true, why nature was engaged in an irreversible process. Atoms had the power to reveal what entropy really was, and why it must always increase. Boltzmann understood that all objects, these walls, you, me, the air in this room, are made up of much tinier constituents. Basically, everything we see is an assembly of trillions and trillions of atoms and molecules. And this was the key to his insight about entropy and the second law. Boltzmann saw what Clausius could not. The real reason why a hot object left alone will always cool down. Imagine a lump of hot metal. The atoms inside it are jostling around. But as they jostle, the atoms at the edge of the object transfer some of their energy to the atoms in the surface of the table. These atoms then bump into their neighbours, and in this way the heat energy slowly and very naturally spreads out and disperses. The whole system has gone from being in a very special, ordered state, with all the energy concentrated in one place, to a disordered state, where the same amount of energy is now distributed among many more atoms. Boltzmann's brilliant mind saw this whole process could be described mathematically.
Boltzmann's great contribution was that although we can talk in rather sort of casual terms about things getting worse and disorder increases, the great contribution of Boltzmann is that he could put numbers to it. And so he was able to derive a formula which enabled you to calculate the disorder of a system.
This is Boltzmann's famous equation. It will be his enduring contribution to science. So much so, it was engraved on his tombstone in Vienna. What this equation means in essence is that there are many more ways for things to be messy and disordered than there are for them to be tidy and ordered. That's why, left to itself, the universe will always get messier. things will move from order to disorder. It's a law that applies to everything, from a drop jug to a burning star, a hot cup of tea to the products that we consume every day. All of this is an expression of the universe's tendency to move from order to disorder. Disorder is the fate of everything. Clausius had shown that something he called entropy was getting bigger all the time. Now Boltzmann had revealed what this really meant. Entropy was in fact a measure of the disorder of things.
Energy is crumbling away. It's crumbling away now as we speak. So the second law is all about entropy increasing, which is just a technical way of saying that things get worse.